Hey everybody, this is the third video for the chapter. This section is entitled Combinations. I've got the definition of a combination on the screen. A combination is a selection of distinct items where no item is selected more than once and the order of the selection does not matter. And it's that last part that distinguishes a combination from what we were talking about in the previous section, which we called permutations. In a permutation, the order matters. The order matters because maybe you're assigning individuals to specific jobs, or maybe you've got a password and you have to put that password in order, or maybe you're arranging objects in a specific way. That would be a permutation. In a combination, the order doesn't matter. Maybe the order doesn't matter because you're just selecting individuals for a committee and there are no jobs on that committee. Every individual has the same role, so to speak, and so it doesn't matter what order you pick the people in. If you pick 3 people, they'll be the same group. Or maybe you're making a purchase and the order in which you make that purchase doesn't matter, right? You're going to a party and you're in charge of buying the chips. I assume people have chips at parties. I don't know. I've never been invited to one. But you're having chips at this party. And so you're going to buy 3 bags of chips. If you buy Doritos and then Fritos and then Lay's, that'd be exactly the same as if you bought Fritos and then Lay's and then Doritos. The order in which those get scanned doesn't matter. You have the same 3 bags of chips. And so that would be a combination where the order doesn't matter. Let's look at an example. We're going to approach this example first by literally listing all of the possibilities and then counting them up. But then I'm going to show you a formula, and we'll see that the formula gives us the same answer as this. Because remember, the whole point of the first part of this chapter is to learn how to count without counting. We want to figure out how many ways something can happen without literally listing and counting them one at a time. So in this example, we've got 5 teams who are playing in a round-robin tournament. If you're not familiar with the concept, a round-robin tournament is a tournament where each team plays each other team exactly once. How many games will be played in this tournament? Well, I'm not very creative, so I'm going to call the teams A, B, C, D, and E. And I want to figure out how many games can be played. And you might have a guess for how many games that will take. But we're going to list them all out. These are combinations because when I come up with a game, it doesn't matter what order I write the opponents in, it's the same game. So like if I write Team A plays Team B, that's the same as if I wrote Team B plays Team A. I don't want to list that twice because that would be those 2 teams playing each other 2 times, and each team's only going to play each other once. So that's one possibility. Another possibility is that Team A plays Team C, and Team A has to play Team D, and they have to play Team E, and that's every game that Team A is going to play. Now I'm going to list the games that B has to play, but I've already listed the game where Team B plays Team A, so I'm not listing that again. But I have to put B against C, and B against D, and B against E. And I have to list the games for Team C, but I've already got 2 of them. Team C still has to play Team D and Team E. And then I need 1 more, right? Because Team D hasn't played Team E yet. And you'll see that every team's been listed exactly 4 times, so they've got all of their games in there. And there's a total of 10 games. That's an example of a combination problem because the order didn't matter. Writing the letters in a different order didn't give us a new game, and so we didn't consider all of the possible arrangements of the letters. We just had to get all of the possible groupings of 2 letters from that set of 5. Now again, we don't want to have to list like this every single time, so we're going to come up with a formula. And the formula uses factorials, just like the permutation formula. It's got an extra little bit. This formula is also loaded into your calculator already, so while I will bore you with doing one by hand, after that we'll do the rest of them with the calculator. The formula says the number of possible combinations of R items taken from N items is given by N factorial divided by the product of R factorial and N minus R factorial. So this one's got an extra factor in the denominator that the permutation doesn't have. We denote this by NCR instead of NPR, but this time we'll do it with the combination formula. It says 5 teams play in a round-robin tournament. How many games will be played? So we need to find all the different ways that we compare 2 of the 5 possible teams. So that would be 5C2. We know it's a combination and not a permutation because it doesn't matter which team we call out first, it's the same game. If I say Team A is playing Team B, that's the same as saying Team B is playing Team A, and so the order in which I announce the teams or choose the teams doesn't matter. The formula tells me that that's 5 factorial divided by 2 factorial times 5 minus 2 factorial. And that's 5 factorial divided by 2 factorial, 3 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, that's 120. 2 factorial is 2 times 1, that's 2. And 3 factorial is 3 times 2 times 1, that's 6. 120 divided by 2 times 6 is 120 divided by 12, and sure enough that gives us 10. Same answer as what we got from listing them out. And you might say, well, it wasn't a big deal to list them out. Couldn't we just do that every time? Well, it probably wouldn't be very advantageous to do it that way if we had 30 teams instead of just 2 teams. Or if we had 15 objects and we wanted to select 6 of them at a time instead of just 2 at a time. So the formula is going to be handy, especially because it's already loaded into your calculator. So if you get your calculator out, we're going to use the same screen that we did before and the same process that we used for permutations. You're going to start by typing the value of n, which is the number of objects you're selecting from. So we have 5 teams to select from. I'm going to push the math key, scroll to the probability heading. Again, if you're lazy like me, you'll want to scroll to the left. Choice 3 says NCR, and as you might guess, that's the combination notation. So NPR for permutations, NCR for combinations. So I'm going to select choice 3. And we're selecting 2 teams at a time. So 2. And hit enter, and there's the 10 that we got using the formula by hand. So from here on out, I'm going to use the calculator. I don't want you to do it this way. You're welcome to, you're allowed to, but I prefer that you use the calculator. What I really want you to focus on is distinguishing between combinations, permutations, and fundamental counting principle problems, and then approaching it with the calculator in the easiest way for you. The examples from the textbook come from page 301. We're going to start with problem number 29. Problem 29 says, an election ballot asks voters to select 3 city commissioners from a group of 6 candidates. In how many ways can this be done? Okay, so now we have to pause because we have to think about, does the order matter here or not? And of course it doesn't, or else it wouldn't be a combination problem. I wouldn't be demonstrating it now. But in the next video, we're going to have them all mixed up, and so we'll really have to think about it. So maybe a better question to ask is, why is this a combination and not a permutation? Well, we're selecting 3 city commissioners with no extra restrictions, like there isn't a grand marshal of the city commissioners or a favorite or anything like that. They all have the same role. They're just city commissioners. So if you're just selecting 3 individuals, it doesn't matter if we select Mary first and then Tommy and then Susie, or if we selected Susie first and then Mary and then Tommy. It's the same 3 city commissioners in the group. And so this is a combination. We have 6 total individuals to choose from. And from those 6, we're going to choose 3 without regard to order. The order doesn't matter. So 6 choose 3, I believe is 20, but let's type it in. I type the 6, push the math key, scroll to probability, choice 3 for combinations, and then we're selecting 3 of those 6 individuals, and yeah, that's 20. So there are 20 different ways that you could select 3 different people. Number 31 says, of 12 possible books, you plan to take 4 with you on vacation. How many different collections of 4 books can you take? So why is this a combination? Again, this should be a combination or else I'm not doing a very good job with this video. But why is this a combination and not a permutation or a fundamental counting principle problem? It's because the order in which you grab the books doesn't matter, right? So you're going to grab To Kill a Mockingbird, and you're going to grab the autobiography of Malcolm X. I'm just looking over at my bookshelf here, and I have a book called A History of Torture, right? So you're taking that one. And of course you're going to take your Math 107 book, right? So those are your 4 books. It doesn't matter if you grab your math book first and The History of Torture second, and then Malcolm X third, and To Kill a Mockingbird last, or if you grab your math book first and then grab To Kill a Mockingbird, and then grab A History of Torture, and then grab Malcolm X. Right? You're obviously going to grab your math book first. But it doesn't matter what order you grab those in. You have the same collection of books. It's the same 4 books regardless of order. So that would be 12 books to choose from, and of those you're going to choose 4. 12 choose 4. 12 choose 4 would have a 12 factorial in the numerator, which makes it seem like it would be really difficult to calculate by hand, but there's actually a shortcut for it. You don't need to worry about that because I would prefer that you use the calculator. So 12, math, scroll to probability, choice 3, and we're selecting 4 of those 12 books. Hit enter. There are 495 different combinations of 4 books that you could select from those 12. So you see why people who like to read have a really hard time deciding what they're going to take with them on vacations, because even if you only had 12 books and you're only taking 4 of them with you, you'd have almost 500 different possibilities. If you had 200 books and you wanted to select 5 of them, there'd be a really large number. I have to bore you with it. Let's see. 200 is probably on the order of how many books I have in my bedroom. I haven't read most of them. It looks like I'm a big reader, but I'm actually just a big book collector. I have read A History of Torture, though. Does that make me weird? Let's see. And if I selected 5 of my 200 books, right, what is this? So, comma, that's 2,535,650,040 different options that I would have to select 5 of my 200 books. If I put any thought into it, it would take me forever. I just don't read any of them. That's my solution. Problem number 35. This one might be interesting to some of you because it's about the lotto. Maybe some of you started playing lottery. I know a lot of you have just only recently become old enough to legally play lotto, so maybe you got sucked into it. I did. I played more scratch off than the version that we're going to talk about here. It says, to win at lotto in the state of Florida, one must correctly select 6 numbers from a collection of 53 numbers. So you've probably seen lotto balls bouncing around. That's typically how they do it, is they have a bunch of what look like ping pong balls getting mixed up, and then 6 of them kind of get rolled out or sucked out or something like that by this contraption. The order in which the selection is made does not matter. In most big 6-number lotteries, the order of the selection doesn't matter. There are special ones like Powerball where you have to get the last number right or something like that. The order of that last one matters. But in this lottery, the order doesn't matter at all. As long as you get the 6 numbers in any order, you're okay. How many different selections are possible? Well, this is definitely a combination because they flat out told us that the order doesn't matter. So there are 53 total balls, and of those, they're going to choose 6 through some random process. So let's see. 53, math, scroll to probability, choice 3, and we're going to select 6. So, comma here, that's almost 23 million. 22,957,480. 22,957,480. That's almost 23 million different ways that the 6 balls could be selected. This is a foreshadowing of what we're going to talk about in the next section. Not in the next lecture, but in the next section, where we start talking about probability. If there are almost 23 million different ways that the balls could be selected, and there's only one combination that wins, that means your probability is about 1 in 23 million. I want to walk you through one more, and in this one we're going to have an added difficulty. This is actually going to combine the ideas in this section with the ideas from the first section. Number 37 says, in how many ways can a committee of 4 men and 5 women be formed from a group of 7 men and 7 women? So here we've broken the groups into 2 kind of subgroups, subsets. You guys know that word, they're subsets. Then we've broken them into the men and the women. There are 7 men and 7 women. And we want to know how many ways a committee can be formed with 4 men and 5 women. So this is combinations because the order in which we choose the men and the women doesn't matter, but it's also fundamental counting because we're making 2 choices. We're choosing some men and we're choosing some women. So I'm going to draw 2 blanks, one for choosing the 4 men. So I'm going to write the number of ways we can choose 4 men in that blank, and then a second blank for choosing the 5 women. Fundamental count says we're going to multiply those 2 quantities together. So how many ways can we choose 4 men from a group of 7 men? Well, since they're serving on a committee, we don't have to worry about the order. That's just 7C4. How many different ways can we choose 5 women from the group of 7 women? Again, the order doesn't matter, so that's 7C5. And once we know what those two numbers are, we'll just multiply them together, and that'll give us the total number of ways we can form this committee. So back to the calculator. 7 math, scroll to probability, choice 3, 4, 7C4 is 35. There are 35 different ways you could choose 4 of the 7 men without regard to order. And 7C5 let's see here, I should be able to do this. What is that, 21? Yeah. And then we have to take 35 times 21. Which is 735. So there are 735 possible committees where you could have 4 men and 5 women selected from the group of 7 men and 7 women. I'll be sure to demonstrate another example like that in Monday's video. We're going to do another video over this section, but we're going to do it for problems 41 through 60, where the 3 methods that we've talked about so far are kind of mixed together. So there are some fundamental counting problems, there are some problems that I would put into the calculator as permutations, and then there are some combination problems. And we'll not only look at the methods, but how we distinguish between the methods. So that's what we'll do next week. Email me if you have any questions.